In this tutorial, we're going to learn how to implement a zero finder using an algorithm called Regula Falsi, which is an algorithm very similar to Newton's method. However, this algorithm is guaranteed to converge to a zero in the function, assuming that the zero is bracketed by two x values. Okay, so here let's open a C++ file, Regula Falsi.cpp. Can include some standard headers. Okay, and declare a templated function. Okay, T is going to be our type, which can be a float or a double, or a long double. This function is going to be the function that we're trying to find the zero of, and x1 and x2 are going to be our bracket x values. So the root is assumed to be between these two x values. And accuracy is the desired accuracy that we wish to achieve. Okay, so first let's evaluate the function at the initial bracket x values. So basically the initial x values are going to be here. So that's going to be x0, and it's going to be x1. So write that here. Or sorry, x1 and x2. x1 and x2. And you see in this case the root is in between x1 and x2. Okay. So we're going to evaluate flow. It's going to be the value of our function at x1, and high is going to be the value at x2. So if flow and high have the same sign, then that's an error. That means the root is not between x1 and x2. Or it could mean that you have multiple roots. That's also possible. But for this case, let's just assume that we just throw an error here, just for simplicity. Okay, so it is possible that we might have a function which is decreasing, so we don't want that. So if that's the case, then we're going to swap x1 and x2. So let's do that here. X low, x high. If low is less than 0, then that's what we want. So we set x low equal to x1 and x high equal to x2. Otherwise, we have to swap. So we set x low to x2, x high to x1, and we have to swap F low and F high. So the swap is going to be F low. F low is going to be F high. F high is going to be swap. Okay, so now we're going to enter the Regula Falsi loop. This is an iterative algorithm, and it's going to iterate until the error is smaller than our desired accuracy. Okay, so t. So first we need to know the delta x and declare some variables such as x-intercept, f value, and error. And now in our iteration loop, we can calculate the x-intercept. It's going to be x plus delta x times f low divided by f low minus f high. So essentially the x-intercept is this point here. So this is our secant line, which connects the 2 points x low, f low, and x high, f high. And wherever the secant line intersects the x-axis, that's when we're going to evaluate f again. Okay, so once we have the x-intercept, we calculate the new f value, which is going to be our function evaluated at the x-intercept location. Okay, so now we need to update our brackets. Essentially, we're going to move one of these boundaries to the x-intercept location. So in this case, since the function evaluated at the x-intercept location is positive and x low or f low is negative, then we know that the root has to be somewhere between these two x locations. So that means we have to move this boundary to the x-intercept location. Okay, so if f value is less than 0, then we get the error, which is going to be x low minus x-intercept. And we're going to set the x low to x-intercept and f low to f value. Otherwise, we're going to move the other boundary to the x-intercept location. So calculate the error, which is going to be x high minus x-intercept. And x high is going to be moved to the x-intercept location, and f high is going to be our new f value. Okay, so now we need to calculate delta x again. X high minus x low, and check our termination condition. So if the absolute error is less than accuracy, or if f value is 0, then we know that we have converged, so we can just return the x-intercept. Check termination condition. Okay, so that's basically the Regula Falsi algorithm. So now let's do a little test. try to simplify main function. And basically we're going to try to evaluate sine of x and find the 0 of sine of x, because we know the answer would be a multiple of pi. So long double root and answer. Okay, so root is going to be Regula Falsi long double sine. So this is basically the sine for long doubles, and we're going to evaluate it at x1 equals to 2 and x2 equals to 4. And the accuracy is going to be 1 to the minus 10th. And let's print out the answer. So the root is going to be root, and then we know that the answer should be pi, so we set the answer to 4 times arctangent of 1, which is pi. So let's print out that answer. Let's see if that compiles. Oh, first we have to write a makefile. So we have to use G++. And let's optimize it. And set the debug symbols to no debug symbols. Okay, let's see if that compiles. Okay, that compiled. Alright, so there you go. Our root was calculated to be pi, and the answer is also pi. So let's maybe print out some intermediate values. So let's say here we print out the intermediate values, and print out x-intercept. Okay, so and then Regula Falsi, we see that it starts out pretty close, and then it gets closer and closer and closer, and finally get our answer. Well, there you go. That's how you implement the zero finder in C++. Okay, that's the end of the tutorial.